So, good morning. Thank you for showing up. I think it's a great forum. I always love when you put this together, Bill. You always have a really great program, and I liked how it started out today with Lisa, and we go to Bill and moving on in the phosphorus side, and we have many more topics to talk about. But I think very interesting the question we had earlier today. I think why are we decoupling or trying to decoupling the agricultural, the municipal biosolids application to agricultural fields? And the answer is really there are two key issues. The first one is the pathogens, which can be fairly easily addressed by going to Class A. But the other one, the big one, is really the phosphorus and nitrogen loading rates. And what we see, what many farmers and EPA and legislators struggle with is how do we have too much, especially now we have very often too much phosphorus in the biosolids and not enough nitrogen. And generally speaking, of course, too much phosphorus is not good. It causes eutrophication, especially when we're talking about Chesapeake Bay or freshwater lakes. And that's really, I think, where people are struggling with. How can we really apply this product, the biosolid product, the Class A product, to beneficial for land use? And unless we change the phosphorus balance in the biosolids, in many cases, it's just not the best idea, probably. And so the good news is there is a solution to that, and hopefully I can point to some of the ways on how we get there. Just a short little story. 15 years ago, I was working in Austria. I was at the University of Vienna, and we had a biosolids conference. And the same question came up to the main starch producer, sugar producer in Austria, a company called Ostara. And in Austria, the sugar is made from sugar beets exclusively. And so they asked the CEO of the company, how come that you don't use biosolids and apply it to your sugar beets? And he said he had a copy of a newspaper article, the leading Austrian newspaper, and on front was a coffee cup, and there was a spoon, and there was a nice white sugar cube. And then essentially said, did you know where your sugar is coming from? And then there was the whole article basically, there's poop in your sugar. And he said, he opened the newspaper in the morning, he said, he got calls from all these people in the company, he said, okay, damage control. And so what they said is from now on, Agrana will not allow biosolids on their beets, on their sugar beet fields. So, that's what we're dealing with. And so, it takes a lot of the public education, the perception is there, and we need to keep educating people on that. So much for that. So, but I'm going in. What I would like to do, I want to show you what's really new on the phosphorus front, on the phosphorus recovery front. Going back now to Europe again, because I think it's just funny what's going on. About 10 plus years ago, Europe said we really don't want to land apply biosolids on our fields for all kinds of health concerns. So they said, okay, let's go. No more land application going forward. We phase it out and we go to incineration. Okay, great. Yeah, let's do it. Scandinavia does a lot of it. And so as they progressed, they also found out phosphorus is a finite resource. So now the problem is the majority of the phosphorus is in the biosolids. Those biosolids get incinerated, and the majority of the phosphorus now is in form of an ash. So people said, okay, no problem, we recover it from the ash. So many people did it, a lot of efforts have been made, but the bottom line is it's super expensive and it's very environmentally unfriendly. So now there's a new law, just been passed about a couple of months ago, saying, so now if you go into incineration, depending on the plant size, larger plants, you need to recover at least, remove 50% of your phosphorus before you go into incineration. And that really sets the bar really, really high in terms of what you have to do in order to get there. So that's where we are. I don't think in the US it's going to happen anytime soon, but the bottom line is people really recover the phosphorus prior to biosolids for several reasons. I will go to those reasons why we do it here in the US. We focus a little more on the US versus Europe. So I have an outline here what we talk about. there's several forms of phosphorus recovery. One is a pre-digestion recovery, one is a post-digestion recovery, meaning we can recover it in front of an anaerobic digester, and we can recover it post-anaerobic digestion. You will see throughout my presentation there are many synergies between, let's say, a thermal hydrolysis process and a phosphorus recovery situation. And in the future, I think we see many more of that. We talk about resource recovery plants where we really, the intent is really to get more, reduce the sludge volume by improving cake solids, like Bill showed us, get more biogas, and also really beneficial to do something with the phosphorus. And then the next front certainly is the nitrogen. How can we cost effectively recover nitrogen? I think nobody has been able to do that. So we go to an NMOX deammonification process, but in the future, that's the next frontier. How can we get a nitrogen-based product? So I'm gonna introduce to you the acid digest phosphorus release. That's a fairly new technology for us. And then we talk about, we did a kind of a research on facilities priorities about resource recovery. So what's important to the utilities? What did they tell us? What do they want to see in terms of resource recovery? Then we speak more about this pre-digestion phosphorus recovery, CalBrex we call it, calcium phosphorus recovery extraction. Then what kind of fertilizers do we recover? What's the difference between brushite and struvite, for example? And then we finish up with Airbrex, which is our classic process, which is post-anaerobic digestion, where we cover struvite and go to some conclusions. So here, when we look at this typical facility, I don't even. Can you hear me in the back without a microphone? Okay, good. Matt, you can hear me? Okay, good. Okay, very good. So when this is a classic, a complete, we would call this a holistic, really resource recovery plant. The main components you see here is a pre-digestion phosphorus recovery. Then we have here thermal hydrolysis, which is the pre-anaerobic digestion system here, what Bill introduced to us. Then there's your anaerobic digester. And then there's another post-phosphorus recovery system, the Airbrex system. So here we have the acid phase B release, separate high solubilization rate of phosphorus, and we use an acid phase digester. We have about 1.5 days HRD in this acid phase digester. We run about pH about 5.5 to 6. We can achieve up to 95% phosphorus solubilization from the total P. We run that sludge, decant it, separate the solids. They go to your DHP system. So preferred we go into a candle like, let's say, 18% or so. We have the cake going to a hydrolysis system, and the phosphorus lead-rich stream is going to a reactor where we dose calcium hydroxide and calcium chloride to precipitate the phosphorus in form of this is now a dicalcium phosphate, brushite. We precipitate it, we settle it, and then we dry it. And what's coming out is the product is called brushite, has about 50% higher phosphorus content than struvite does. So when you go to facilities which have a post-digestion or any other process, they struggle really with getting the biosolids content here down on the dewatering step. And the issue is, if you don't go prior to anaerobic digestion, you just cannot get the type of recovery above really 30-35% OLP recovery if you do it post-digestion or even with another form of fermentation process. So if you're really serious, and the legislation tells us to really hit 50% of more P recovery in your biosolid, you need to combine a pre-digestion and post-digestion recovery process. And then here, the product is about, commercially, brushite is worth about $300 a ton, struvite is about $100 a ton. Unless you market it like Ostara does, it's the Corp, then of course you can achieve more money for it. But phosphorus prices are really low right now, and I think a very important point I always make and I want to make is, we do not do this to produce a fertilizer. That's not why we are doing this. We do this to get rid of struvite We do this to really cut out the recycling loads back to the front of the process. We do it to improve the waterability by removing the phosphorus, and yeah, those are really the main reasons. The fertilizer is nice; it helps us on our ROI, but it's not. You cannot make an economic case with current today's phosphorus prices. By of course, elimination of ferric or alum and polymer. Yeah, exactly. Thank you. So it was interesting, when we go on this acid phase. When we looked at this, there are not about, I think I want to say in the US, maybe 30, 40 facilities which have an acid phase digester. And historically it was a good thing, then it was a bad thing, and now all of a sudden it's a good thing. And when we talk to facilities, especially larger facilities, they are really now, a lot of folks are really considering building acid phase digester. Miami, South District is considering building acid phase digester in order to really have increased VFA production, and also really have a high orthophosphate reactive B-solubilization with acid phase digester. So the classic, the bigger ones are of course here Madison, and Ostara process is operating in Madison. Denver, Denver is going to install a post-digestion air brake system. So they're designing around air brakes right now. So that's going to be implemented in end of 2017-18. So that's very, for us, obviously the largest project yet. So, but they're also looking further down the line. Bill mentioned it, into hydrolyzation, and maybe then also a pre-digestion phosphorus recovery. And then of course Hampton Roads, you have a system there, Kent has a system there, there is also a phosphorus recovery system there, so the Hampton Roads sanitation district also has an acid phase digester. So we see much more interest of and this is exactly why people build acid phase digester. So if you're serious about recovering phosphorus, then look on the left. On the left are my soluble ions during anaerobic digestion. On the left hand side is the acid phase digester, then here we have the thermophilic digester, and then mesophilic, and then we have the filtrate. So if you are really serious about extracting phosphorus, you go here. This is where you get a huge amount of solubilization. We have seen solubilization rates 95%. Minimum is 55, and then we go up to 95%. So if you don't get the phosphorus out right at the beginning, at the front, you never can get it out later from your biosolids. You need to resolubilize, you need to get the ortho B first in the solubilization, and then you can recover it. So, so the three forms of phosphorus minerals. So the first one is brushite. That's what you will get from acid phase digester by dosing calcium, and it's dicalcium phosphate. It forms at around pH of 4.5 to 6.5. It's a very good fertilizer, very good high phosphorus content, about 18%. Then we have struvite, which is, all under magnesium ammonium phosphate. Some of you who have experienced struvite in your plants are in the digester after it forms when you have magnesium ammonium phosphate. Forms at a pH of around 8. It's also a very good fertilizer. And then we have hydroxyapatite. So when you dose, and that's like a quicklime or something like that, when you dose lime into the process to drive a reaction very quickly, you get the form of phosphorus. But the problem is, at a pH of 9, this is not a very good fertilizer. It doesn't have a very good solubilization rate. So in terms of fertilizer, this is an inferior product. It's not as good, by far not even close to struvite or brushite. So I mentioned earlier, so when we look at people, so what's important to folks who want to do resource recovery? So, and those are really the points we got, and really this is more on the biosolid side. I don't have biogas up here for my hydrolysis, but it kind of ties all into it. So we have reduction of phosphorus loads, because when you down about 1/3 of a total P load is coming from your centrate or your filtrate back to the front of your plant. So when you get hit with low effluent limit rates, if you don't get out the ortho B from your filtrate, you're not going to meet the liquid level. You really struggle there. And then 80% of the total payload is in the waste activated sludge. So that's why we really need to go and get it out from the biosolid, from the sludge before it goes back to the front of the plant. Struvite control, pre and post digestion. If you want to really have a digester eliminate majority of the struvite, you have probably a pre-digestion phosphorus release. If you can deal with a little digester precipitation, you just do an air breaks, a post digestion, which is more economical, much simpler system. A big one for us is when we developed the airbox system, the main objective for us was the dewatering improvement. And we see that, it's European driven, but also in the US. What we have seen is when we piloted at the big plants, when you have a BioB plant, airbags versus non-airbags, by removing the phosphorus, post anaerobic digestion, we gain about 4 percentage point in cake solids. So for a Denver Metro, that's obviously for larger plants, it's significant. What we also have seen is that the polymers can be reduced by as much as 30%. And that's really coming from the fact that when you have a BioB plant and struvite formation, you deplete the divalent cation. Your magnesium gets taken up and forms struvite. And so you don't have magnesium available to form a flock later on. So by dosing magnesium, overdosing it a little bit by forming in the reactor, you re-establish this balance, and then you can dewater your biosolids again to the fact what you've done before. So in a large utilities case like Denver, that's a savings of about $750,000 a year by reducing polymer consumption by 25%. So it's a big one. And then that's the next point, improvement of nitrogen to phosphorus ratio in biosolids. That's a big topic for somebody like for many of you know the from Mallory from Milwaukee Metropolitan. The issue they have is really having consistent nitrogen and phosphorus loading rates. And most problems with most folks who produce like a fertilizer from the biosolids, they have too much phosphorus and not enough nitrogen in that fertilizer, and they would love to change the balance. And by removing the phosphorus, pre-digestion or post, now you can re-establish this balance. You almost, if you will, customize it a little bit. You give it more nitrogen and less phosphorus in your biosolids, so it becomes more marketable, more valuable. And then the final one is the phosphorus recovery to produce a valuable fertilizer. Yeah, well, I think Bill addressed it really well. So here we are. So that's now hydrolysis and nitrogen. So that was all addressed. Energy production, solids destruction, lower disposal costs, and ammonia removal recovery. We right now, everybody's working, and we do as well, trying to cost effectively recover ammonia, nitrogen. But the truth of the matter is right now nobody has been able to do it commercially. So most people go to an NMOX deammonification route to get rid of ammonia. But we will get there, and we will also have the next product we have from like a hydrolysis, a special hydrolysis system. We will be able to cost effectively recover nitrogen and phosphorus. And then you really have a self-sustainable resource recovery facility where the energy balance of that plant will be positive. The whole plant, I'm not talking about biosolids, and the entire plant, including aeration. When you look here, different systems, on the left is the potential for phosphorus recovery. I mentioned a little bit. On the left, we have the recovery potential of total P. I'm talking total P here now, from 0 to 60, 70%. On the bottom, we have the solubilization rate. So this is really critical, because if you don't solubilize the P, like the water P, you cannot recover it. So what we do is when we look at conventional system, and you see, I'm picking out here like CNP airbags, which is our classic post-anaerobic digestion system. We go up to about, we get up to probably about a recovery rate of maybe 23% or something like that. Ostara, the wasp goes up to maybe 30%. And then it's over. And then when we go to acid phase, then we really start, we go up all the way. We have hit, 60+%. So if you have a resolubilization of 100%, then you would have about 65% total B recovery. Obviously not, that's a very ambitious goal, but we have seen solubilization rate of 95% and pretty typically 85%. So 50% target, like in Europe, is doable. But right now it's really only doable if you do something like an acid phase pre-digestion solubilization of phosphorus. Okay? So we mentioned again here the picture again. So here would be my acid phase pre-release. Low pH coming, the centrifuge separation, liquid solids, solids to pH3, digester, brushite formed here. And then after the digester, we have normally the air brakes. This reactor is designed for 10-hour HRB. So when we already recover about 80% of the B, we leave a little of the ortho Bs in the digester, just maybe 50, 60 milligrams. And then after the digester, we have a very small 3 to 4 hour HRB air brake system. We aerate the tank with those magnesium chloride, and we precipitate the remainder of the phosphorus in form of struvite. So we come out here with 5 milligrams of B, so ortho B. And then in the biosolids, I recover total B for somewhere around 50 plus %. So now here you have the fertilizer, you protect the digester. We have here the improvement in tolerability, reduction in polymer consumption, and overall speaking, we have a reduction of recycling loads of about a minimum of 90% here, going back to the founder of the plant. And ultimately, now this is now addressing all these issues which are shown, which is struvite control, the recycling load interception, and eliminating the phosphorus from the biosolids. So when you do both of these systems, you achieve that. If you do this one, it's hard to maintain a very extremely low P limit after the attrition. If you just do air brakes, obviously now you still have some struvite formation in the digester, but obviously nothing after this air brakes rate and the devolving improvement of this. So really air brakes is really well suited for smaller to mid-sized plants and can go to large plants, but if somebody wants to have everything, then this would be really the whole combination. And I think if somebody is going to like a PHP system, then this is the whole system makes a whole lot of sense looking at all of these components. So that's a Calbrake, so calcium phosphate recovery. So we talked about that. Yeah, and really importantly, and I don't want to diminish the value of brushite or struvite. Clearly, both are extremely valuable fertilizers. So the Calbrake technology came out from the University of Wisconsin in Madison, and what they looked at is 10 years ago they looked to produce a fertilizer, organically derived fertilizer, and then came. And they looked, where can we find brushite? And of course the answer was, wastewater. So they start looking at it and did a lot of research. And what you see here on the graph is here, you see here these plants, they all have been fertilized with brushite, with monoammonium phosphate, and with triple superphosphate. And those are the dosing rate in milligrams per kilogram. So what you see is this is no application of the plant, and then they fertilize this plant, and you see there's really not different in growth of the plants, of the three plants, regardless of whether you dose monoammonium phosphate, diammonium phosphate, triple superphosphate, or brushite. So they are very similar in the fertilizer properties. And here is another picture where struvite is very good already, but it's not as good as brushite because of the lower phosphorus content. And then you have monoammonium phosphate, diammonium phosphate, and triple superphosphate, which are a little bit better, but statistically it's insignificant. So brushite is a very good substitute for triple superphosphate or MAP or TAP. So this is air brakes now. We did a lot of pilots during the last 18 months. I think last year I was talking about the dewatering improvements. So now we have all the results in. So what you see here is it's basically, I call it a pilot, but it was really a full-scale pilot. So we ran a reactor, and we ran a centrifuge on about 12 different plants. And the way we set it up is we use anaerobic digested solids. We ran it through the centrifuge for 2 days, measured dry solids concentration, polymer, centroid quality. We ran this sludge in 2 days to the airbag system, here to the reactor where we dose magnesium chloride, remove the phosphorus, the water B, and convert it to struvite, and then run that out of the reactor to the centrifuge to see what impact does it have on dewaterability, on cake solids, on polymer concentration, on the centroid quality. And then the struvite gets washed in this is like a modified, a little similar to Huber grit washer, remove the solids from the struvite and gets discharged. But here is what we've seen. This is the graph. So the main message here is what you see is that this blue curve, the light blue curve, represents regular digested sludge. Here's a dry cake solids concentration. Here's the polymer concentration, polymer demand. And what you see is here, let's pick a pound, I'm just saying here, let's say this is 40 pounds. So regular digested sludge, 40 pounds, you get 22% or so dry solids on bio-based sludge. So when we use air brakes, we run into air brakes, remove phosphorus, we get up to about 26%. Or if you say, okay, I don't care, I want the same dry solids concentration, so get 22%. How much lower can we reduce polymer concentration to get us to 22%? And in Denmar's case, that was about 30%. So we have achieved pretty significant savings, low 2%, high 5%, and polymer reductions of 10 to about, as high as 50%. I think that was Arizona, Tucson, at some of these plants. So it's a huge savings. This is really what pays for air brakes, and it's a very simple system. It comes after the anaerobic digester. You can implement it always later. Gary, I don't know if you're gonna talk about Miami tomorrow, huh? Okay, yeah, okay. So some of the installations, the birthplace of air brakes, those are air brakes, post-digestion. The birthplace was Berlin in Germany. It's about 120 MGD plant. Really, they did it for dewatering improvement and reduction maintenance. And then the largest one is Amsterdam. That's about 170 MGD plants. That's in operation for about 2 years. And then you see we have some smaller plants from anywhere from 5 to about 30 MGD. And all of them are running about 3% extra dry cake solids and have their polymer reduced by about 30%. And nobody experienced any maintenance issue anymore with struvite in their plants. The product there is sold for about $85 a ton to fertilizer company, which offsets the really in Europe the purchase of the magnesium chloride, which is fantastic. In the US, we pay a little more for magnesium chloride, so you have about an offset. If you get $100 a ton, you probably can offset about maybe 50% of your cost for the chemical, which is your main operating cost system. So, and here's my conclusion. So acid phase digesters are really effective tool for phosphorus release. So if you want to recover a high amount of phosphorus, the acid digester is the way to go. If we combine pre and post digestion phosphorus recovery, we can achieve a super high total B elimination. We can also get two products, struvite and brushed, and we have improved dewaterability. And then brushed and struvite are both high-grade fertilizers. And 28 minutes and 57 seconds. Look at that, I made 1 minute up.
Well, he has 1 minute. Take a question. And we have Lisa.